Welcome to exercise number 9. It's about evaluation of improvements of PV modules. We'll talk about three different types of improvement, about optical improvement, thermal improvement, and about lifetime extension. First, we start with the optical measure. An anti-reflective coating is added on the surface of the PV module. It increases optical transmission, energy weighted by average of 3% over the whole day. And the first question is, for which parts of the day that measure works most effective, considering a standard installation that means orientated towards south at a module elevation of 30 degrees. Why is it so? For perpendicular incidence, it's towards midday. We have an incidence angle of 0 degrees that you see here. You see here also the different curve. That is, the blue curve is with an anti-reflective coating, and the gray line is a normal class. You see here there's not much difference at perpendicular incidence, but if you go towards larger incidence angle, you see a difference here. So for midday, this is not very effective. So the difference between with and without RC is relatively small. You can derive that also by the Fresnel equations, as I shown you in the optical part. But if we go towards a large incidence angle, that means if we go towards the morning and the evening, then we see a difference, and the difference becomes bigger. So it's more effective in the morning and evening hours. So a second question of that part is, does it make economically sense if such a layer costs 10 euro per square meter, considering a module efficiency of 17%, that would cost 30 cents per watt peak? What are the maximum extra costs for that measure, considering the upper parameters given? Are there impacts on the BOS, that means balance of systems costs? So the RC makes sense if the gain and the related costs would be cheaper than the cost for additional modules offering the same amount of additional electrical energy. So 1 square meter of module costs, so we can calculate that we have A as one area of 1 square meter, and it receives in standard test conditions, because also the power is related to standard test conditions. So we have here 1000 watt per square meter, the irradiance under standard test conditions, and also the module efficiency, which is usually given under standard test conditions, 17%, and the area is 1 square meter. And then we have 170 watts and costs of 30 cents per watt peak. That is 51 euro of 1 square meter of PV module. It's just a copy of the last transparency here, and then we have 3% gain in transmission and also in energy, and that would mean we have a value of 1.53 euro if we would add additional modules, and the costs of 10 euros per square meter are more expensive for RSC, so it doesn't make economically sense. Maximum price is 1 euro and 53 cents, then it would make sense. Are there impacts on the BOS costs? The RSC would not extend the BOS costs, and contrarily we need less PV modules and would reduce, but only slightly, the BOS costs. If we would have additional module area, we would require some additional BOS costs. Third part of the question is here, what will be the effects on the electrical output parameters on voltage, current or power? So the anti-reflective coating is increasing the number of photons that reach the PN interface in the solar cell, and so it increases the number of electrons being generated, and therefore is increasing the current and therefore also the output power by about 3%. There's no significance on the voltage. Okay, you can consider a bit reduced weak light effect because you have effectively more irradiance. But on the other hand, the temperature is a little bit increased due to higher irradiance value, so probably it compensates, so let's say there's no significant impact on voltage. Let's come to the second measure. We have thermal measure, a new backsheet material with an increased thermal emissivity reduces the operating cell temperature by 2 degrees, and for which parts of the day that measure works most effective, considering a standard installation, that means also orientated towards south at an elevation angle of 30 degrees. And why is that so? Let's go back to our model, our thermal model. We see we have increased thermal emissivity, and from the thermal heat flow we want to increase that, and this sure depends on the thermal emissivity factors, but also mostly on, this is a front sheet, this is a back sheet, and here we see it strongly depends on temperature by a power of 4. So the emissive power is proportional to a power of 4 of the temperature. So the higher the temperature, the much higher is the thermal radiation emission. And therefore that measure has the best effect at highest temperature, and that occurs from midday towards the afternoon. We take a look at the temperature curve here, and as you know from the lecture, and if we take a look here, it's about from 11 a.m. to 2 p.m. Second part of that question is, does it make economically sense if such a layer costs 10 euro per square meter, same price here, and module efficiency also at 17%, module costs at 0.3 euro watt peak. What are the maximum extra costs for that measures, considering also the upper parameters given? So temperature reduction is already energy weighted, so otherwise we would have to calculate the power output for each day separately, and considering actual irradiance, temperature, and so on. So the power and energy in this case is, we put it in relative terms. So the relative increase in power, so we have a reduction in temperature by 2 Kelvin. We have the temperature coefficient for power, which is in this case minus 0.5% per Kelvin. So that leads to a relative increase in power output of 1%. So the backsheet material, the new backsheet material makes sense if the gain and the related costs would be cheaper than additional modules offering the same amount of additional electrical energy. So again, 1 square meter of module costs here under standard test conditions, and we have an efficiency of 0.17 times 1000 watt per square meter. That's the irradiance under standard test conditions. So the power under standard test conditions 170 watt, and that module would cost 170 watt times 30 cents per watt, 51 euro, same as before. And an additional 1% of module area would cost then only 51 cents. So, but if you have to pay 10 euro per square meter, that's much too expensive. So it would only make sense if the costs would be lower than 51 cents per square meter. So what will be the effect on electrical power output parameters such as voltage, current, and power? So the temperature reduction leads to increased voltages and output power, and negligible reduction in current. So if you remember the curve, the IV curve with a temperature variation, so the dashed line here is under standard test conditions, and if we reduce temperature, we move towards the right part. So we have an increased voltage here, and also if you take a look at the green points, these are the maximum power points, and also the maximum power points at reduced temperature go to a higher voltage level, and altogether we have a higher power output. The power is determined by voltage times current. you see that at the lower voltages the current is very slightly decreased, but this doesn't matter. The main effect is the increase in voltage. So we have about an increase in power, which is about the same value as the increase in voltage. You can see this here also, the temperature coefficient. We have a relatively high temperature coefficient of minus 0.5% per Kelvin. Here you see some other material. So this is typically for multicrystalline silicon, 0.44% per Kelvin. Depends on the manufacturer and the exact process parameter you have. So in this minus 0.5% per Kelvin is on the safe side here. So last question is talk about lifetime extension. So we add a phase change material, for example, on the back sheet, and that reduces thermal stress. That means the variation of temperature is less because it acts like a thermal mass, and so the increase or decrease in temperature is much slower, and therefore the solar cell interconnectors and leads are less stressed, and therefore lifetime extension is increased from 25 to 30 years. On the other hand, the thermal conductivity of that PCM material is not perfect because we have a reduced heat flow on the backside because we have an increased thermal resistance here, and therefore the operation temperature is increased and energy weighted by 3 degrees Celsius, and the temperature coefficient should be the same as before, minus 0.5% per Kelvin for temperature coefficient of power output. First question is what effects do you expect during the course of the day, also considering a standard installation, and yes, to the reduced thermal conductivity, temperature increases, voltage is reduced, and also power is accordingly reduced linearly. So again, this picture here from the AB curves, at increased temperature we move towards left, so at lower voltages, and also accordingly towards a lower maximum power points. If you take a quick guess, so 3 degrees at 0.5% of losses here, with about 1.5% less in power output. Here, so relative losses are minus 1.5%, while it's energy weighted, so it's energy loss of 1.5%. But it's there's an explanation for it, that the PCM, come to this a little bit later, I'll show you an example. The PCM reduces cell temperature as long as PCM is still melting, so we get more power in the morning, but in the midday and afternoon all material is molten, and the PCM is not of any more use. We only have the effect of a reduced heat transfer because we have a higher thermal resistance, and therefore altogether we have decrease in power generation. But lifetime is extended. Let's see how much this effect is. So again, the question, does it make economically sense if such a layer would cost 10 euro per square meter? Module efficiency again, and under standard test conditions at 17%. Module costs for 1 watt under standard test conditions is 30 cents. What are the maximum extra costs for that measures considering the upper parameters given? So temperature increase, we have calculated that already. So that's a loss of 1.5% in energy, and we got, while lifetime is 5 years longer, during that time energy is still produced, so we get a gain here, relative a gain in energy being generated. That's the duration of the lifetime. So new lifetime 30 years, and we got an increase of 5 years divided by 25 years, so we got a gain of 20% in lifetime, and accordingly in energy being generated during lifetime. If we consider the losses here are due to the higher temperatures, then we altogether got a gain of still 18.5%. And in order to compensate that, we at the original configuration, we should add 18.5% of modules, and these modules cost per square meter 51 euros, and this cost would be for 18.5% of more energy would increase the cost per square meter of 9.18 euros. So we are very close to 10 euros, but still it doesn't make economically sense, only if we stay below that value of 9.18 euro per square meter. What will be the effects of the electrical on the electrical output parameter, voltage, current and power? So in the morning we have reduced temperature, so voltage will be increased and we would have more power. In the afternoon, when all the material is molten, the PCM is of no more use. It will even increase temperature due to the reduced heat transfer. As I mentioned already, we have a higher thermal resistance, and we have then less power and less voltage. This we tested already, so we see here the time of the day. It's a bit not visible, but here is 1 p.m. Summertime. That is usually sun time. It is midday here, and this is the irradiance of a clear day in Paderborn. And we see here in the morning the module is quite cold when sun goes up, and with the PCM material it stays cold. We used two different kinds of PCM material at that example. We used standard PCM material and a material called PCM Plus, indicated by red color. That means we put some additional additive in the PCM that increases the conductibility, thermal conductibility of PCM material in order to reduce thermal resistance, which is especially relevant in the afternoon. Let's see the results. So here for the PCM material, it soaks up the heat, so we have a considerable energy gain in the morning, but irradiance is quite low, so it seems very impressive here, but this is just relative energy gain difference. And this goes down, and here we have still some gains here, but in the midday and afternoon the impact of the PCM material is negative, especially for the pure PCM material without the heat conductive additive. And here we see for losses in the afternoon. It's not very big, below 5, in the yes, about 5%, and in the evening it gets bigger because it's heating up, and then the reduced conductibility, thermal conductivity is getting more important. So therefore you can explain that. So we have here in the morning we have a higher voltage, in the evening we have a reduced voltage. Altogether we have a power and energy loss of what we calculated here of 3% of 1.5% less production, but the main advantage is here the increased lifetime. Thank you very much.